Oh, perfect. Thank you. I don't see you on this, but I will try to do what I can. Let me share my screen and you guys take a look at it. You can see it. Can you step, I still have a screen share access.
Device in the body and then led.
Okay.
In the submit on that. The negative key. Press 1 to see you.
Okay. Can you guys see this?
You do this list.
Perfect. So everyone, super excited to be talking at PyCon. That was the last time I was at PyCon. It was the first PyCon back in 2017. And I'm really glad that, we're building this community in Pakistan, people who are really into the technology. I'm going to talk a little bit about something that is very close to the work that I do. As you heard in the introduction, I work on NLP. I'm a PhD student there. In fact, I've been doing NLP for a long time. And something that is a very fundamental part of most NLP pipelines is finding similar things and getting LLMs to generate better outputs, right? So I will be doing what exactly is needs. So the title of the talk is Semantic Search Retrieval Generation with LLMs. But essentially, the topic is how do you find what you're looking for and get LLMs to do what you want them to. These are like the two fundamental challenges in working with something like this. So the first thing is, it's a really exciting time to work with AI and AI products and LLMs because there's two reasons. The first is that we're generating lots and lots of data. Pretty much every product and service we use is generating tons of data. And now we have to compete with as well to make use of that data. And also LLMs are getting very smart, right? Where every week you see new advancements in either existing LLMs or you see new ones coming up. So you have OpenAI with the newer, better version of GPT every few months. You have Anthropic, you have Cohere, you have Mixture of all these amazing LLMs. But there are still some fundamental challenges with trying to build these products that don't stop the industry. So you have tons and tons of companies popping up in pretty much every vertical, every niche you can imagine, using LLMs and lots of data to build like a very interesting product. This could be consumer facing or business facing. But there are two major challenges, and both of the advantages we talked about in the beginning, where you have lots of data and LLMs are getting very smart, they both have the caveats, right? So with lots of data, the main problem is finding what you're looking for, right? There's this really common experience people have had in recent years with Google search, right? It's like you might look what you're trying to look for, the answer, the results will always back. Now that is driven mostly by their profit incentives. They want to sell ads and not give you what you're looking for. But finding the right results for search queries is still a long-standing challenge. So we have tons of data, but how do we find what we're looking for within that data? And the other is that LLMs, as anything as they are, can do hallucinate quite a bit, right? So there's only so much knowledge you can go into the, few hundred billion parameters that most LLMs have right now. And human knowledge and internet in particular is like much larger than that, right? So you have like trillions and trillions of tokens. You really can't memorize all of that. You actually really want to memorize all of that. But there are some questions where you want to go back and see exactly what was said somewhere in its knowledge base, right? But they get these answers wrong quite a bit of time. So hallucinations again are a big problem with LLMs and make these up. So how do we solve this, right? So again, it's the same thing I talked about at the beginning. The first is we can solve this step by step, right? The first thing is let's first think about how we can find relevant documents, and then think about how we can use them to make the LLMs more accurate. So the first thing is finding what we're looking for, right? We have tons and tons of data. We have a search term or a search query, or we have, let's say, a query document that we want to test against that data. And just how do we do this? So this has been a long-standing challenge in order to research for a very long time, right? We call it semantics, which is essentially semantics meaning, right? So we're trying to capture the meaning of a piece of text. And it's not as straightforward as you assume, right? Like a decade ago, you have, if you have to like represent all the words in a vocabulary, you can have like a really long vector, which you have zeros at every index and a one at the position of that word. So, cat would be 0, 0, 0, 1, and then it would be under zeros, and then dog would be a vector of the same size where the one would be in a different position. We would call this one harmonic coding. But that isn't great, right? Because there's no relation between the cat and dog being differences. The similarity is that going to be they have a one in the vector and it's in a different position, but there's no way to do that to find the one data first. The same problem exists in documents, right? So you can imagine you pick some of Shakespeare's plays. One way that we have classically done this in NLP is look at all the words in the documents and then count how many times they show up in each particular document. And that gives us like a fingerprint about what this document is talking about, right? So as you like it, those lines you can see 0 headed to the fifth. You look at how many times the word value shows up in each of those grades, in each of the documents, right? You look at the word good, how many times does that show up? So Phillips Knight has the word good in it 80 times. As you like it has it in its document 140 times. And the word like quick is a little more rare. It only shows up in you see it like twice, and then as you like it 20 times, right? And once you have these vocabulary counts for all of your documents, this is basically like a long vector. You can like map them into like an n-dimensional space, and the n here is basically the size of your vocabulary. If you have 50,000 words in your vocabulary is going to be across all of the documents you have. You basically have a 50,000 dimensional space where you can like map each document as a vector in that space. So if you were to purely compare these documents based on the frequencies of the word battle and food, you would see that Engelbert and Julius Caesar are sort of similar because they have the same ratio of the words battle versus food. They talk more about battles versus foods because they are about kings, and kings tend to go to battle quite often. And then as you like it, you might talk more about foods than you do about battle, right? So that's a different subject. So that's one way we have possibly tried to find similar documents and then cluster them together. But it isn't great because there's a problem with category mismatch, right? So you might have different words meaning the exact same thing, but they aren't the exact same matches. So if you want to look for like love stories about, an tragic love story, for example, but Shakespeare writes about a star-crossed lover, none of the words are the same, but we know that they essentially mean the same thing. And that's what we now want to resolve, right? Because if I want to like write a good search framework, I need to be able to resolve the meaning of the search term and then compare the meaning of the documents I have in store. And this is where word embeddings and dense representations come in. Everyone's probably heard of word embedding already. It's something like 11 years ago, about 2013, and something very again before that, where you basically made these very dense representations where, king is not just a long vector with a 1 at one position and a 0 everywhere else. It is like a very dense vector with lots of floating point numbers across all of them. And these dense vectors are trained out between yield, but they're trained in a way that the space that they map these vectors in captures the semantic meaning of these words, right? So you can use a linear algebra to find relations between words that have similar meanings. So, king is seen as maps of woman, walking and walk, swimming and swam, and then also some relationships like country and county, and you also the strength, and that is amazing. For a long time, though, this was only limited to words, right? So you could only get an embedding for one word, and then you could get an embedding for another word. And there really wasn't a great way to get embeddings for entire sentences for documents. Now, with the word, many years ago, we started to use language models and started to get representations of longer sentences. They were still limited. So Word has a input limit of 500 tokens. And that basically translates to about 200 something words, right? Token is like about 3/4 of a word the way to do that example. But Recent advances in LLMs have really expanded the context limits of these models. So BERT, which is very famous and basically changed the NLP landscape, was only 5 algorithms, right? That's like 5 figure words. But OpenAI's embedding model, for example, right? It has a context limit of 8,000 words. So you can embed 6,000 word long documents in one pass. In the past, you would basically have to embed each and every word individually and then do a average of them, but that doesn't really work great because you can't collapse the meaning of an entire document into the same number of dimensions. So this has been very interesting, right? Now you can embed large sets of really long documents and then do document level comparisons with each other. So the way to do this is really simple. You can essentially, if you use the OpenAI API, it's really simple. Put your API key and base line for it, send in your text, and it will give you back and embed it. You can also use other models. I know, kind of so an OpenAI model here, but there are other models as well. The bigger ones are almost all paid. The smaller ones like Semantic and other variations you find open source on our base. So let's say if you want to work with documents, right? So you probably be using Cohere or GPT. So we send our text to the model and we get in response an embedding. So on the left is what these dense embeddings are like, right? It's not the same, all the zeros and then it's one at one particular position for a word. In this case, the embedding is essentially a very index vector of all fully defined values. And its size is also much larger than we had previously with word embeddings, right? Word embeddings usually use time to be regular dimensions, linear dimensions, or linear dimensions. But now with these document embeddings, we have up to 1,500 dimensional, and the newest model that was released 4 weeks ago goes up to 2,000 dimensions. And this is useful because you can model the meaning of a word into the dimension, but it's hard to model the meaning of an entire document in the same number of dimensions. So you really want more space, and literally more space in the dimensional space we're talking about to model the meaning of a document. So, and these are actually pretty cheap as well. So you can get these embeddings back right here that representing the meaning of that particular document, and you can look at how you can actually use them later on. But they're actually quite cheap as well. So if you can use the paid OpenAI API, you can embed in tokens for 2 cents or 13 cents, depending on the model you're using. In the same time, later on, we'll use the text embedding the small document model. In my work, I work with news articles, so you can embed a million news articles that are each about 700 words for $100. Which is very nuts, particularly if you're a corporation. You can really understand systems to this. And once you have these embeddings back, all you do is do a cosine similarity comparison. So you might call embeddings are vectors, and if you want to compare vectors, there's like 2 basic ways in math. One is the equilibrium distance, where you look at the exact, a squared plus b squared, a squared, all of that. Actually, a squared minus b squared. But if you these embeddings, generally what we use is the cosine similarity. So this is basically the angle between these documents. So if your documents, as we saw in the beginning, if they're very similar, the angle between these 2 vectors is really small, and if they're very different, then the angle between these 2 vectors is very large. So this is how we can essentially compare the extract the meaning of the document and also find similar documents. Use like meaning values and similarity under this. And once you've done this, for like let's say lots of documents, it starts to really interesting patterns appear. So this is an example from one experiment where we collected a bunch of news articles from some time ago. And if you do all the pairwise comparisons of their embeddings using the cosine similarity, you will start to see the hotspots show up, which are essentially all the topic on the same article. So the first cluster here is about the Hawaii wildfires happening last year. The second one is about Supreme Court and their rulings on gun restriction, etc. and so on. So right now, if you look at these embeddings, you can go to like really powerful document clustering systems, right? They did not really have a few years ago. You would almost have like try to document into smaller pieces or like break them on tools before you could get anything like this done. And it also works across languages. So I know the GPT mostly identifies itself as an English-only model, but you can actually give it anything. As long as it's really good, you can give GPT like any string of text you want, and it will give you back some kind of code. It might not make much sense, but if you write this text in a language that the model has probably been enough to have it depending on pretty much a significant amount of the internet. You can actually use the targets across languages. So there's an article like off of the internet some time ago, and kind of divided it into 2 different languages. So we have the English, and then we have French, Spanish, and German. And you can still do these comparisons. Now, obviously, the English to English is like 100% right. The similarity is perfect because it is exactly the same document. But even across languages, we still maintain a fairly high level of similarity, right? So English French is a fun language, English Spanish is a fun language as well. And same for English German, because these are all like any time you say about any like Arabic or Urdu or language that any one of those aren't training on, you do not get very high similarity. But this still shows that in this semantic space where you can get all of these pieces of text, there are all like subspaces for different languages, and within those languages there are subspaces for different documents. So even if you wanted to do, let's say, you want to include the permission treatment system, you could do that with these embeddings. You would not have to translate something from Urdu into English and then do some kind of string matching or word similarity. You can basically just embed the original itself, and then as long as you translate granting it together with English article, you can still get it as one results. So that's really powerful, right? You can model documents across topics, across languages, and still maintain relations between them to the vectors. So what does it look like in practice, right? So let's say I'm building a semantic search system for any kind of a user product or database that I have. And for example, let's use the Amazon Food Reviews data set. You've got like a long list of reviews on the website, the product maybe user rating, how many stars it is given by the user, and then also like text of the review. So we have the text of the review. From that we can get the embeddings, and once we have the embeddings, all we need to do is give it a search term of our own. So let's say I want to look for cat food, right? What I would do is I would get an embedding for cat food, and then go over all of these embeddings in the database, compare each one of them, then sort them by similarity and pick the top one, right? So the highest rank column will always be the one that is similar to what I'm looking for, and then that is return as my result. And so what I would say in practice, so let's say I look for religious fees, right? One example from OpenAI. Just searching for that, like those two terms alone, can literally find things that are really not really exactly similar at the lexical level. So the lexical level can be a word of comparisons, but still have the exact same meaning, right? So if you were to build a dumb, TF-IDF style search pipeline, you were basically looking for the word delicious and beans, 20 negative times. And this is sort of similar, but also better in a way that someone could say tasty instead of delicious, and you still get that as one of the results. Someone could add a few other adjectives before the parts you're looking for, and as long as they're positive and if you're looking for is positive, you still find matches in there. So you can search for something like this, and it will give you all the right reviews. You can search for, let's say, whole wheat pasta, and it's not looking for the exact phrase. It's actually looking at the meaning of what I'm looking for, and then the meaning of what the documents or the reviews it already has contained, and then find the ones that match it, see the best. And these are like really useful things that we can use. And I think most of you are understand probably people who work in the industry. If you're working with data sets, to study something you can incorporate into your frameworks. But as you're thinking about steer to the thought, the main question on your mind would be, right now when I'm doing there is like a comparison where like the ridiculous follow that case embedding of the search query and goes and compares it with like every embedding of every retrieval data set. As databases scale, this is not ideal. And this challenged the goal in how do we find the right how do we do these embedding similarities has led to this entire like project industry of startups that are focused purely on this thing, right? And they've been raising the kind of funds. It's not like last year with these startups that have raised hundreds of millions of dollars in VC funding. And they come in all different flavors. You have different source ones, you have paid ones, you have some ones that come with a freemium model, which you can use a free version if you want to get a better functionality, you have to pay for it. So these are great, and a lot of times you can see people talk about them, like launches about them, and applications and how to use them, and these companies certainly push their part quite a bit. But they don't necessarily need them just for making something of your own. So it's an example that I just found on my computer that it says it's an empty maps with just 52 gigs of RAM. And even like running a MacBook, you can compare like 50,000 vectors, like all petabytes comparisons within about 30 seconds. Like on this, I'm not even done the actual statistical timing by any one of the runs. This is one run you started from the initialization to the end. And that's actually what I've been doing in my work as well. I've not yet needed to use these big databases. You can just do basic comparisons with NumPy inside anywhere, and they actually very efficient because of the numerical computational libraries that you can implement it are very, very fast. So you can actually implement a decent-sized semantic search pipeline on your computer. And when I say that 50,000 documents can compare 50,000 other documents and go all database comparisons, so essentially it means that if you were to relate this to giving the system one search query and compare it with the sort of instead of like all of all things to one versus all of seven, this would be like 50,000 times 50,000, which would be probably like 300 million searches that it can do within like 30-40 seconds on your computer. And then you can get that as a response that indicates where the database that tells you like all the similarities, the numbers, so the similarity of all of these documents. If you're one, it's probably one of that because that's like document IA, comics, document J is exactly the same. But the other ones are more extreme ones. I think if you really scale systems up, there are libraries that are open source. The one that I have found very useful is Annoy. It's by Spotify. Spotify, I imagine, probably embeds music. So these systems are also used quite a bit in recommendation systems. If you want to like make recommendations based on users' task activity. So Spotify has a good library called Annoy. It actually really stands for approximate layers neighbors called that's just clean and sort of like YAM a little bit in the modern language. And what these do is they don't do these dumb comparisons of your search with every other entity in the database. They do it with kind of a pre-structure, right? So the approximate layers neighbors, it is statistically correct in the like large number unit, where if you run it for a distinct size amount of data with certain parameters, the results that you get might only be pretty much the same as what you would with an exact search, but you come up more efficient. So they do these like big trees over the entire data space, and then they can find the shortest path to the exact item you're looking for, instead of having to do all kinds of comparisons because they know which neighborhood it's in. They basically make this situation of the entire space so they know where to look for instead of doing that comparisons. So that's great, right? So we looked at how these you can actually embed in the documents and find similar ones. But then how do you like use this to make LLM more accurate? So I talked a little bit about LLM hallucinate. There is a limit to how much information they can remember. And there's two problems, right? One is that they made things up because they just don't remember, what the exact thing that data was that they were trained on, which they shouldn't actually remember, right? That's perfectly fine. And then also, if they're training cutoff, for example, for GPT, the training cutoff is almost always equivalent to a year from today, right? So it's like forward data. So if you were to ask us right now, what is happening in Palestine, it would probably not have much information on that. So we want to be able to give LLMs this information ourselves, right? So one good thing about LLMs is that they're good at instruction following. They've been trained primarily as instruction followers. So you can give an instruction and say, hey, forget what you've been taught. Just use your common sense ability, and then do what I'm giving you and answer my question based on the information that I'm giving you. Right? And that's basically what you would ask if you to do as well, right? You give them a syllabus, you give them like an open book exam, you say, just use your innate intelligence to read what's being given to you in this document and answer your question. And this is a paradigm called retrieval augmented generation that I found quite fascinating and I've started working on recently. Instead of only relying on the information that LLM has, what you do is essentially what we've already done, right? So in the first step, let's say you have a query that says who is the president of the US. You would embed this query in the same way that it just did for the Amazon food reviews data set or the document that we embedded, right? So this thing could be a document, a query, could be any string that makes sense. You would embed this string. And then the retriever would basically be the same kind of efficient nearest neighbor vector similarity search system that would also have embedded, let's say, all of the media or whatever your knowledge base is, right? If you're working in a corporation, you generally have secreted documents that you want to train your own systems on, and you don't want to get them to OpenAI, or you don't want to fine-tune them. You can build systems in-house with all these comparisons that are done locally, and then you can send the context off to the administrator level provider, so it doesn't have access to all of their data. So you get a search query embedded. You also have embedded, let's say, all of Wikipedia or your knowledge base. You do all the comparisons between them. You find the ones that are most similar. So let's say you're looking for who's the president of the US. I imagine the most similar Wikipedia pages are going to be about president and the United States government and maybe Biden or Trump or Obama. You can sort them by similarity, but let's say you get an order list of them, you pick the top, let's say 3 or 4, and then you can give them to your model as context, right? So you say, so the initial query would have been in the previous paradigm, who is the president of the US, and the model gets this wrong because it doesn't know who the current president is. In the current paradigm, you would not give this query to the LLM, you would basically say, who is the president of the US, and then you would append the documents, and then you would read the query, you would read the documents. And then the answer that they would get would be more accurate. So it's a really helpful tool for keeping LLMs more up to date and also customizing them based on your own knowledge base, which I'm sure people would obviously want to do because GPT is not working all times. And then it's actually what is really practice as well. So if you search something that GPT knows is not currently found on the internet, on any knowledge base, you could go on the internet and search for that. It could bring that query document to all the constituents and then go on the internet and find the documents that are related and then bring them back to these documents and answer your query. This is an example of asking who won your search. And then you can also do similar analysis of the same thing in code as well, where you, if you have used profiles with dev setups, that's actually what they use as well. They get all the snippets of code and then they recommend similar ones to use, so you're more looking at the right thing exactly customized for your use case. And in practice, it looks like very similar. So you would basically, if you ask a model something that is out of its knowledge base, it would refuse to answer, or say you can have a real-time example you can run yourself, asking your model, which after this one, what happens is a mix, maybe just doesn't have it on that. But then you can just get the Wikipedia page for those relatives, give the raw text without formatting just the Wikipedia or markdown Wikipedia, and then say, use the URL below, answer a specific question, and then answer the question, and then it gets the answer right. So this is like a really powerful RNA that you actually find useful in your work. And you can go up and do it. I will stop talking because I will be the back of the conference today right after my talk, which is the lunch, which is the dinner. And you get a video for that, so I will keep you on. So now you can actually go off and do this on your own. I hope this was helpful. I will put the code for this on GitHub, so if you get any notes, it's all fine. I have a saved notebook and it walks you through all of these examples of the various things in there, showing you how you research over identities and sort of LLMs. Yeah, I will stop there. And if anyone has any questions, I can see the audience, so I'm happy to repeat that. Thank you.
Perfect. And there is sign working. We have already an art side, previous weekends over an art side, art side down here. So just one or two questions very quickly. You guys the novel. Did anyone have a question? Any questions? One or two at the room this second. And you are good. Change reaches people.
Perfect.
Thank you, Samar, once again. And really a round of applause.
I can't really see them, but I assume you will. Great to be at PyCon, have fun at the Retrieval conference. I wish I could be there in person, but if anyone wants to get in touch, you can find me on the internet, and I will chat more about their families and everything else.
Thank you so much.
Okay.